I want to welcome the whole team and kind of kick off Chris's research. Chris Flint Shadow is with ZGF Architects, and his work on advancing net zero design in medical facilities is super important because it's not a building type that we've seen a lot of net zero energy and carbon work in. And I just want to say personally, it was a fun fellowship for me because Chris and I worked together on ZGF's sustainable design team back in the early days of that work. And as you can see, he's still at it and advancing new research and initiatives to really advance the market. So exciting for me, and I will let Chris introduce his team. But I first just want to give a shout out to Katie Anderson, who worked with Chris on this. But Katie is also a past fellow through Energy Trust Net Zero Fellowship Program, and her research is now several years old, but you can find that on the website as well. All right, so with that, why don't I turn it over to Chris and you can introduce the rest of the team.
Yeah, well, thank you. We're really happy to be here and talk about the feasibility of net zero energy in outpatient facilities. As Naomi and Kriya were saying, well, I had the honor of being officially the Net Zero Fellow. I want to acknowledge and thank the contributors who are here on this call. We really did this as an integrated project, really to try to really represent what it would take to achieve net zero energy from an energy performance perspective and a cost perspective. So I'm really thankful for our colleagues who we worked with on numerous healthcare projects. So a lot of expertise here, both Lyle and Katie here with AEI doing the energy modeling, and the mechanical design aspects of this. Eric and Philip from Swinnerton Construction, who helped really with the costing that underlies the life cycle costing and the feasibility. And my colleague, Jennifer Jones, a project architect here at ZGF with a lot of healthcare experience. So she was instrumental in really diving into what it really takes programmatically to make an outpatient facility. And I also do want to acknowledge too that as part of this project, really in terms of scoping what an outpatient medical facility is, and as you'll see, there's a lot of actually variety in that. The participation of Legacy Health, Peace Health, and Providence, the individuals listed here, were really instrumental in helping us understand the diversity and how we could make this project as representative as possible to this unique building type. And through this project too, we were able to engage a number of other architects who work in the healthcare sphere who are listed, as well as some students at Portland State University at the outset who are involved in their research-based design initiative. So an opportunity really to bring in students at the ground in this research and expose them to some of these ideas too. So it was a tremendous year of research. And so again, we're very thankful to the Energy Trust of Oregon for supporting that, and really happy for this opportunity here to present it to you today. So thank you very much. So why are we doing net zero energy healthcare? Well, one, this is a typology, as I mentioned, that the folks here in this call all have a considerable experience. So this is actually helping inform how we think about our future projects. It's also true that healthcare is a large part of our domestic energy usage and carbon impact. 8.5% of greenhouse gas emissions, 10% of our annual energy usage. It's the second largest energy use in the US and one of the most energy intensive types. So it's important as we continue to adopt efficiency and try to decarbonize our building energy usage to address healthcare. And it's actually one of the most challenging types. This is data from the AIA 2030 commitment, something that ZGF and many architecture firms participate in, tracking and targeting zero carbon design by 2030. And we've made less progress in healthcare than most all other typologies. So it's an area that we need to focus on more. It's also a sector that is ripe for transformation. Many healthcare institutions have signed onto this healthcare climate sector pledge, pledging to reduce and offset their carbon emissions associated with Scope 1 and Scope 2, which is essentially and largely the energy usage of their facilities. So both direct combustion on building level and electrical energy usage. So many of our clients are targeting being essentially net zero. So doing a net zero outpatient facility seems increasingly on the table. 10 years ago, maybe healthcare was not as much adopting this type of next level energy efficiency, but we're having these conversations now. So this seemed like a good building type to tackle. And I think part of the reason healthcare institutions have signed on to that pledge and increasingly looking to push energy efficiency further is that they realize that climate change is a public health issue. Heat waves are causing increasing deaths, unfortunately, in many areas with extreme temperatures, smoke, wildfire smoke, et cetera. So this connection between our greenhouse gas emissions and public health is increasingly apparent. And so healthcare institutions, as being part of the solution on the healthcare side, can also be part of the solution to help reduce the impacts of future catastrophic events. And finally, we recognize that as part of the overall economics and business proposition of healthcare, healthcare services are increasingly moving from inpatient hospital facilities, which tend to be very large, maybe existing facilities, and incrementally changing, and increasingly moving a lot of these services, including surgeries, to outpatient facilities. And there's a lot of economic and healthcare distribution, bringing healthcare to further, non-urban regions doing this. And as part of this, many of these outpatient facilities are new facilities. And so there's an opportunity with these new facilities to potentially push energy efficiency and target net zero energy. So it seemed increasingly relevant for that reason as well. So now we're going to talk just a few minutes about sort of the methodology and how we studied this. And as part of this, I'll turn it over to my colleague, Jennifer.
Thanks, Chris. Yes, so pivoting to the methodology here, one of the primary goals of this study was to provide as wide a range of applicability as possible for this typology, particularly for freestanding outpatient facilities, which there are a wide range of services that could be provided with an equally wide range of energy intensity based on the service mix within the building. So to capture this variability, we've organized our study into 3 primary programs for analysis. This first program on the slide here is the medical office building, or more commonly referred to as the MOB, and generally the lowest in terms of energy consumption due to the primarily housing doctor's offices and exam rooms for a variety of primary care or specialty care clinics. We've assumed about 70% of the outpatient clinic dedicated to clinics with some support space and a typical grossing factor. And note the blue color used here. This is a clue that this is an energy use that is typically less energy intensive and therefore cooler. And then at the opposite end of the spectrum here of the outpatient facilities is the outpatient surgery facility, or ASC. This program is dominated by operating rooms, procedure rooms for minimally invasive procedures, and some portion could be attributed to sterile processing or imaging, which is very intensive. So we've used a similar area for support and grossing factor here, and note that this program is red. So this is the cue that this is the most energy intensive, the hottest of the programs. And then our third program here is a blend actually of the blue and the red, hence the purple. And it's commonly referred to as the ambulatory care center. So you've got both ends of the spectrum represented here, from the specialty care clinic all the way to the outpatient surgery.
And I think maybe one other thing to point out here too is that the square footage here, these are all a little bit different. This building essentially is adding both of those programs, so almost about twice its size. But we carry that sort of square footage throughout the whole.
Exactly. Yeah. In this next slide, you can see the 3 compared side by side. You'll see that these total square footages at the bottom are different, and that's partially based on the way that we set up our energy model so that it could be all stacked into one model and then analyzed separately. But the important factor here, and we want to make sure that it's understood that a lot of our metrics are based on a cost per square foot so that we can make a reasonable comparison between these programs. And then here we have, we wanted to address the influence of climate on the building performance. So our study also considers 2 primary climate zones within Oregon. So we've selected the most populous of each zone, Portland for the marine climate of zone 4C here in the blue, and then Bend for the drier climate categorized by 5B in the pink. And then here we're looking at PV as it relates to the site configuration, just noting that there could be a variety of site restraints on the project. And for your urban site, you are most likely limited to the rooftop of the building for your PV array. Whereas with the more suburban environment, you have a much greater ability to provide PV within the parking area with a structured canopy. So you can see that if we're just talking about the rooftop, you're getting about 440 kilowatt array just on the rooftop of the building. But as you expand that over the parking lot, and what we've demonstrated here is about 11 acres or so, you're getting 6 or 7 times what you would get off of your rooftop. So a substantially greater advantage from the ability to generate energy for this type of site. Before we get to this, I did want to note just one thing that I forgot on the last couple of slides. The intent here is really, though we sort of represent 3 programs, the study is not suggesting that you choose between these programs in order to make an informed decision, but rather that the information is helping you make decisions about investments for your project that might make the most sense given the program requirements. For going back, Chris.
All right. Good morning, everyone. My name is Lyle Keck with AEI. My colleague Katie and I worked on the energy analysis and mechanical systems optimization. And this graphic on screen here illustrates the team's design approach for the path to net zero energy, really starting at that larger top of the pyramid and working our way down. So the first step is to look at applying demand reduction measures in passive systems. Things like improved envelope, reduced internal loads, and even operational strategies like temperature and ventilation setbacks all reduce the need for energy. Applying these measures first allow us to reduce the amount of energy needed over the course of the year, as well as reduce peak heating and cooling loads to really unlock more efficient space conditioning systems such as radiant heating and cooling or natural ventilation. When you get kind of to the blue part of the diagram here, the next step is to apply energy efficient active systems such as heat pumps and decoupled HVAC systems that deliver that energy as efficiently as possible. And then the ultimate goal at the bottom is to bring the energy use intensity low enough so that you can offset the annual energy use with renewable energy generation and kind of minimize that capital cost and embodied carbon associated with renewables. So what we found is that on every project, there's sort of this inflection point where further investing in energy efficiency becomes less cost efficient and more carbon intensive than just procuring renewable energy systems to meet that EUI. So we're always kind of looking for that inflection point or balance point, and Chris will share some of the charts later, kind of talking about this idea. And so as a team, we developed 3 energy efficiency bundles consisting of envelope, lighting, equipment and process, mechanical systems, even operational strategies. And these measures were grouped together in bundles and then tested against the other project parameters of climate, program, and site configuration. So quickly talking through these, our baseline is kind of a code compliant and more of a standard practice here in the Northwest. Which is a pretty decent starting point given how progressive the energy codes are relative to other parts of the country. In the middle, we have the better bundle, and this does represent more of kind of a best practice bang for the buck set of measures based on our team's collective healthcare experience. We developed a set of measures to achieve significant energy savings with a moderate increase in construction costs. And I'd also just like to point out that this better bundle includes a fully electrified system with heat pumps and a backup electric boiler. And then on the right-hand side, we have the best bundle. So this is how we really sort of push things further to see how low the energy use intensity would go with solutions that are practical, but still kind of considered cutting edge for many healthcare providers, and with a cost premium that is really much greater in magnitude to the overall project cost. So I'll hand it over now to Katie and Jenny, and they're going to talk through some of those strategies behind these bundles.
Thanks, Lyle. This is just to sort of orient us, this is the snapshot cutaway of the purple program. So it has both the MOB, the sort of lower intensity program at the bottom in blue, the first 2 stories, and then the second 2 stories roughly are the surgery center. So the combination is that blended program we were talking about. We're just showing the blended program so that we can go through all of the measures that apply to each area. Some of them only apply to either the blue or the red. So you can infer where you would that there would be some changes if you looked at just the blue or the red. So this is the baseline system, typically aligned with energy code, like Lyle said. There's the option for photovoltaics, but our baseline didn't include it. I'm going to focus a bit on the mechanical system description, and then Jenny will talk some about the envelope. So the baseline system, the majority of spaces are served by a single VAV, so return air system air handler with zonal reheat. And there are some exceptions to this, some back of house spaces that are served by fan coils, like electrical mechanical rooms and an IDF room. But for the vast majority of areas, it's just one air handler. And this is a baseline because it is a lower expense mechanical system. It meets code, but as we'll talk later, there are some big downsides in terms of controllability and operations that have energy impacts. So we assumed Energy Star equipment, and which in our experience does not have a cost premium. It is a gas-fired hot water plant with water-cooled chillers, and there are no big airflow setbacks in the high airflow requirement spaces. Okay.
And then in terms of the envelope performance, we have assumed R21 for the walls, R30 for the roof, and then we're also showing in this section a 45% window to wall ratio, which is quite generous, but pretty common.
Okay, when we start looking at the better bundle, we've made some increases to the efficiency of the lighting, but the big changes in terms of energy use on the mechanical side is that we have switched the plant to air source heat pumps and heat recovery chillers. So the baseline has air-cooled chillers and gas boilers. Here we have heat recovery chillers and air source heat pumps. So this is a fully electrified design, and the heat recovery chillers are really key in the healthcare space because of the high airflow requirements that are there for regulatory purposes. So the high airflow requirements mean that in most cases, you will have a significant amount of simultaneous heating and cooling happening in your spaces. And the heat recovery chillers allow us to achieve that conditioning at a pretty high efficiency level. The other big change for the mechanical systems is that in the better option, we've segregated some of the areas. So we now, instead of that one big VAV with reheat air handler, we have segregation between the MOB has an urgent care that has longer operating hours than the normal office areas. So the office areas would run sort of 7 a.m. to 7 p.m. and urgent care is 6 a.m. to midnight. So when we segregate those air handler systems, we can more effectively turn off the main MOB air handler at 7 p.m. And so that results in energy savings. Similarly, in the surgery program, we can segregate the imaging and the OR sections. The OR section is segregated so that the rest of the surgery program can have a lower filtration requirement, which reduces the fan power required, and it also allows overnight shutdowns in the non-OR section, because the ORs are required to have those high airflow requirements overnight. In addition to that, we have included operational setbacks overnight. In the ORs, they can go down from the required sort of 20 air changes per hour to 6. So that's a big decrease, and that has, that's not a cost add, but it is an big operational change that is very beneficial. And we've also included some temperature setbacks.
And for the envelope here, we're assuming a higher insulation of the roof with an R50 roof and a higher insulation of the walls with R30. We've also reduced the amount of glazing to see to start to understand the delta between the wall ratio percentages. So this one is represented with 35% window to wall ratio. It's still quite generous.
Okay, finally, for the best program, we've done an additional lighting power reduction. In terms of our operational settings, they're basically the same as the better programs. We've got those big airflow setbacks that are really helping us in the ORs, and the plant has been upgraded to a a ground source plant. So it has a higher efficiency than but it still has the heat recovery, and that's the big change for the plant side. On the air side, we've upgraded the main air handlers to a DOAS, so a dedicated outdoor air system with active chilled beams in the zones. This isn't allowed in all areas for outpatient healthcare, but in the areas where we are allowed to achieve those minimum air changes per hour set by the regulatory requirements, in the areas where those are allowed to be met by active chilled beams, we've placed active chilled beams. So in exam rooms, for example, you're allowed to achieve the air changes via the induction from the active chilled beam. And so you can reduce the primary air that's coming from the air handler, which results in fan and conditioning savings.
And architecturally here, we are assuming an R50 roof, the same as the best strategy. I'm seeing an error here in our walls. It should be R30 for this scenario. And we also have a reduced wall to window ratio of 20%. We've also improved the windows here. So we're showing a triple pane glass and thermally improved fiberglass frames.
Okay, so this slide shows a summary of what's been discussed in terms of the climate, site location, and program options when we did the analysis. And so it summarizes all of the things that you sort of are predetermined before you start designing the building, meaning the location, the end, the program. Those usually come to a design team predetermined, and then the performance model options, the base, better, and best, that we've applied to each of those scenarios. Okay, this shows the energy results for Portland. So I'm doing first a deep dive into the Portland results, and in a little while I'll show the Bend results side by side. But this is a detailed breakout of all of the baseline results for Portland for the different programs. So at the bottom you can see the MOBs in blue, MOB plus the surgery center in purple, and then in red at the far left is just the surgery center by itself. So this is just to get us oriented to the difference in energy use intensity that the program has. You can see that the blue MOB starts a little under 70 kBTU per square foot, whereas the surgery center starts at almost 105. So that's an increase of about 50% compared to the MOB. And when you look at the breakdown of where energy use is, you can see that there's a big increase in fans, for example, which makes sense. As you go to the left, there's an increase in fan energy, which makes sense based on the higher air changes that are required by the surgery program, as well as the overnight operation that's required. Okay, go to the next slide, please. You can see here the improvement in performance when we go to the better bundle. You can see there's a big decrease in fan energy in gray, as well as some decreases in the lighting based on improved lighting, and then the heating and cooling are shrinking really significantly. So at bottom, the pink and the black are the cooling and the heating respectively. They're going down really significantly. And most of that improvement is due to the operational improvements on the mechanical side. So we do the setbacks overnight in the surgery center, and we can reduce the hours of airflow delivery in the blue due to segregating more of those, the air handlers, so that we can have better controllability of when things are on and off, as well as on the plant side, we have those heat recovery chillers. So all of those things are contributing to a big improvement in the amount of plant energy used, the pink and the black. Okay. Go to the next one. All right, so this is comparing the previous results to the best results, those premium systems that we were discussing. You can see that there is an improvement, but it's much smaller than the improvement from base to better. So those premium systems are really about how low can we go in order to minimize the amount of renewables that's required if we're really trying to get to net zero. We're confined by, we can't necessarily get as many renewables as we need based on site constraints. So the premium systems are really about how low can we go. But the large improvements that we see from base to better are really about operational and including that heat recovery on the plant side. Those are a really big deal. Okay, good slide. Okay, so now this is showing the comparison between the Portland and the Bend results. So you can see, just for example, let's focus on the surgery in red. You can see that the base is very similar, 104.8 to 104.1, and that trend continues as you do the improvement. So what the results showed us is that the location, the climate zone, when we're talking about Portland versus Bend, is not a huge driver. They're relatively similar. So energy results can be generalized pretty well from this study to the rest of our state. Okay. And this is showing the energy results for the different options compared to, in gray, the photovoltaic, the PV array potential for the urban and suburban sites. So you can see, as Chris alluded to earlier, that the urban site is constrained to just the roof area, and the suburban has a much higher PV availability because you can do that parking lot mounted, site mounted solar. So it can, when you look at the suburban in comparison to the actual EUIs we were able to achieve in the better and best options, the suburban site does start to be feasible in terms of achieving that close to zero EUI, whereas the urban, it's much more challenging.
Thank you, Katie. Yep. So that first part, really kind of diving into our program and really into just the dynamics of renewable energy. We anticipated that net zero energy would be really challenging for a roof constrained or site constrained urban medical office building, outpatient facility. So this idea of looking for renewable energy either on the site with a large parking canopy, or potentially for other projects that are site constrained or economically constrained, we looked a bit at sort of off-site renewable procurement. And so we settled on these three, and I want to make a couple points here between them. One is that the cost is variable. So, about $3.70 a watt for a rooftop array, just about twice the amount of that for a canopy, and that's largely because of the infrastructure. The steel canopy is intensive to hold the PV array over an automobile, where you wouldn't have to do that on a rooftop array. That's not just a cost driver, but it also substantially increases the embodied carbon. We'll be talking about carbon considerations in a little bit. And so part of this, in realizing the economics and the site constraints, we also looked at what might be some offsite renewable energy procurements and really investigated a virtual power purchase agreement. This is an agreement where an institution can contract with a utility scale renewable provider, either in that same utility grid or in the continental US, and basically get an agreement where they agree to buy the difference in price between what that virtual provider is selling their renewable energy and where they're drawing their energy from their utility. So essentially, it may be zero cost depending on the price of electricity difference, but these are long-term contracts. Some healthcare institutions across the country are doing this, tend to be larger institutions, and there may be economic advantages, but there's also economic risk depending on the trending differences in renewable costs. So it's hard to say exactly what the cost is, but day one there's no first cost impact, and it really sort of locks in an electrical rate over the future, and that economics would change depending on the economics of the energy cost. So very different, both in terms of the first day costs. In an embodied carbon, we don't have numbers for the virtual array because they're wildly variable, but we'd suspect it'd be less than what would be for a provider to put renewables on their site, because it's a larger scale, more efficient. These tend to be ground mounted, and so less infrastructure. I'll turn it over to my colleagues from Swinnerton Construction to talk about their efforts to do life cycle or first costing to inform our life cycle analysis.
Thanks, Chris. This is Eric Benedetti. I'm the healthcare lead for Swinnerton Builders here out of our Portland office. And first, I'll kind of talk a little bit about how we approach this task. Philip and I have worked with ZGF and AEI on projects with similar programs in this area. So we had a good amount of data to work with, as well as engage some of our trusted trade partners in the area. In addition to that, Swinnerton has a national healthcare group, and so we're always updating our metrics for conceptual budgets that we can always tap into. Philip and I created a price per square foot based on program that allowed us to easily modulate the overall cost based on the amount of square footage dedicated to a particular program, whether it's the MOB, the ASC, or the combined thing with the support spaces. So after we created that overall cost, we evaluated based on the two build locations, Portland and Bend. These are on the higher end of building cost locations, even relative to a lot of the areas on the West Coast. So that's worth noting, as well as the level of finish contributed to the overall cost. On this slide, it's pretty busy. I do want to point out a couple things here. There is an error on this, so pardon that. We can distribute a revised version of this later, but along each bar, you'll see a number written vertically, and that represents the price per gross square foot of that particular building and baseline better best build. The colored bars represent all the different upgrades. Though the error is that those colored bars should actually be breakouts within the black portion or the direct cost portion of the building. So the numbers that you see on the left-hand side of each bar, those actually represent the total price per square foot of the building, including the upgrades that are noted in the different colors. The only thing that those numbers do not include is the additional cost for developing a full site, as was mentioned by our colleagues earlier, and the cost of the site PV. So those are represented by a beige and a light blue color. Those are not in the baseline cost per gross square foot. I'll turn it over to my colleague Philip to talk about some of the idiosyncrasies between the two, or actually all the different options that are represented here.
Good afternoon, Philip Thrash, Chief Estimator with Swinnerton. I won't go too far into the details, but we'll highlight some of the cost-efficient options that we priced as part of the study. So for the good, better, best options, when we looked at the electrical systems, we saw as you go from baseline to better to best, we saw a linear increase, which was great because that's predictable. For the mechanical systems, we saw an initial increase of, let's say it's $30 a square foot, but then to jump up to the most efficient, best option, it was another $35 to $40 a square foot for the additional geothermal pumps, the site development, the more efficient system. So overall, those were increases that were going in a linear, with which we would expect. When we look at the envelope, what we saw was interesting because the window costs, although they were increasing, going from like a dual pane to a triple pane, the cost per square foot for windows goes up, but because your envelope is decreasing how much window area there is, the cost wasn't linear. The impact to go from baseline to best was about $5 a square foot, and then to go from best to or good, excuse me, better to best, it was only a few dollars a square foot. So you really get a good return on your investment for that initial base to better, and then going from better to best is also an increase, but not as much as going from the first to the second step. For exterior walls, it's the same thing. The exterior wall would go up, but not in a linear fashion. The increase would flatten out. The roofing going from R30 to R50 was a baseline to better option, and that was one cost increase, and then going from better to best, it flattened out completely.
Okay.
Yep, and more details can be seen in that report if you download, and we'll open it up for questions afterwards.
Yeah, and we'll reissue this chart in the report too, so folks get the corrected data. So I apologize about the visualization there. I do want to point out, as Eric and Philip were talking about, one of the fundamental dynamics here, that as we go from baseline, better, and best, the overall cost is increasing with each bundle. The only thing that was reducing was that the window cost. And so this is because these healthcare outpatient facilities are very system intensive. We're meeting the current regulatory codes and practices, providing a high level of patient and practitioner safety with ventilation systems. So unlike other typologies, say like an office or a residential building where we'd be tunneling through the cost barrier, and as we're getting efficiencies in envelope, being able to eliminate systems, this was one of the fundamental challenges of this project, that these higher level of efficiencies are coming at an increased cost. We're not able to eliminate systems, and so our overall cost is increasing dramatically, or significantly, I should say. So now I'm going to pivot to the life cycle cost analysis, and this provides an overview of our assumptions. So we did this on a 25-year basis, which is a reasonable proxy for the lifetime of the equipment. And so we assumed the equipment would last for that 25 years, and we did not retain any residual value, resale value at the end of that life. In some ways, this is overly simplistic. Some of these systems, particularly ground source, could last a lot longer. We also assumed a 2.5% annual maintenance cost for those systems. And so what happens with more expensive systems, right, is that associated maintenance would also be an increased annual cost. That is, again, a somewhat simplistic assumption, but beyond the scope of our project to dive into that deeper, but that could be refined. We assumed a 1.2% energy escalation. There's a lot of predictions out there about the future cost of energy. This seemed like a good reasonable input. And we assumed a 3% discount rate for future cash flows. When doing net present value, you need to put things in current future dollars. This seemed like a good value based on what healthcare institutions see, but every institution might have a different assumption here. And we did calculate this all in real dollars, so we don't need to predict future inflation. And then we use commercial utility rates, and for Portland we used PGE's rates, and for Bend it was Pacific Power. And we also included the ETO incentives and considerably the path to net zero incentives. So targeting with this program and achieving over a 5% predicted energy use savings, 25 cents per kilowatt hour for the first year savings and 80 cents per therm. And then they increased to 40 cents per kilowatt hour and $1.20 per therm, achieving an 80% ratio, getting 80% of the way to net zero. So now we see, without the numbers here, but just the graphics, the overall dynamic. So we see our two locations, Portland and then Bend on the right, the urban and the suburban scenario for our three different programs. And we're taking our base, we're adding the photovoltaics to that base level, and then we're hitting our better and best packages. And what I want to point out, overall dynamic, these numbers are the net present value, is that overall net present value is increasing in each case. So we're not seeing a savings. Again, and some of that is driven by the increased systems cost, building cost at first on day one, not being able to sort of tunnel or eliminate systems. And also you can see that the cost of the annual maintenance cost is more than our energy costs or more than our energy savings. So that is hindering us from essentially paying back on those energy savings. And that's driven, recognizing we do have some of the cheaper commercial energy rates. We're blessed with that in the Pacific Northwest, makes it more challenging in this type of typology where we can't eliminate systems to achieve those energy savings within these bundles as we define them. So now just diving in a little bit more for just our Portland scenario, we can see sort of those life cycle costs. So we're seeing in bottom, you can see notated those costs of the energy trust incentives, which are considerable, and in some cases approach to almost $1 million or more, depending on the overall use of that facility, and help pay for the energy costs, but those first costs and maintenance costs are still driving, based on these assumptions, the overall net present value, making these scenarios not pay back within those 25 years. And this is another way of looking at it. So this is really comparing, looking at moving from our base and now just looking at the MOB. On the left axis is that energy use intensity that Katie was talking about, our energy per square foot. And so starting at around 70 kBTUs per square foot for our base. And now when we add PV to that, you can see we reduce our EUI, but that energy cost is going up. We're paying for that PV. And you can see that for the suburban scenario where we have parking lot canopies, we're essentially, in Bend, we actually achieve net zero energy. With Portland, we fall just short, but we do that with an increased cost in net present value. Now we apply efficiency, and we are further driving down our EUI for our urban scenario for this building type. And actually for the suburban MOB, we actually achieve it in Portland. And I want to point out, actually, we are achieving some net present value savings here because the cost of those energy efficiency is low. We are able to reduce the cost of that parking PV array, which is fairly expensive per watt. And so the size of that array goes down, and we achieve some net present value savings. And then when we apply that best scenario, we can see really moderate, small EUI savings and a somewhat significant cost per square foot in net present value. So now we look at, it's essentially the same dynamic for our purple program as well, and then for the ambulatory surgery center. So again, so achieving net zero for all of the suburban scenarios, but seeing an overall cost per square foot on a net present value basis. Now I want to pivot for a minute just to talk about carbon considerations, because we're increasingly concerned about the operational and embodied carbon. We'll talk about what that means in a second, but looking at our facilities and the greenhouse gas emissions associated with energy use. So we use data from NREL's Cambium tool. And this is showing for the current year the CO2 content, the carbon emissions per unit of electricity. And I want to point out that the Pacific Northwest, of course, has some of the cleanest electricity currently in the US, just about 30 kilograms per megawatt hour on average, sort of on par with California and the Northeast. But we wanted to also predict future emissions. So we looked at different cases in Cambium, and we looked at, these are sort of look at the middle case, a worst case for renewable energy, where renewable energy is in the future is less cost competitive compared to fossil fuel, in a best case. And these are the Cambium predictions for the overall Pacific Northwest greenhouse gases per square foot. And to say there's a wide variety or variance in carbon is not surprising. There's a lot of uncertainty about this. Hopefully we're moving more towards the green scenario. But for the purposes of this study, we decided to take the mid case as sort of an average emissions factor. And now we're looking at that emissions factor for 1 year, for the current year, and looking at those hourly grid emission factors in gray, and then comparing for our suburban larger PV array, what the overall PV production would be in kilowatt hours. And so what I want to point out on the grid is you can see moderate measurable carbon emissions January, February, March, but over the summer from April through July, there's essentially no emissions. And this is because our grid is largely hydro and renewables. So we start to see come July and then increasing in August and September as those hydro resources are depleted and more fossil fuels are coming on the grid, that emissions increase dramatically through the rest of the year. With some variance, of course, during the day based on renewables being produced. Of course, PV being the most largely affected by that. But I do want to point out that there is some synergy in that in those August, September, October months, which are some of the higher grid emissions, this is a time where the PV is actually generating still a fairly considerable amount of energy. And so there's a real potential for that PV to displace those grid emissions during those months. So now we took our scenarios and calculated the net balance of greenhouse gas emissions. And this is our baseline scenario. And we can see the hourly grid emissions in gray, and then the accumulated net annual emissions. So over 250 metric tons of carbon emissions from this scenario. And now we compare this to the better scenario with PV, and we can see that actually, again, August, September, October, our project is helping displace grid emissions, so actually reduces the net annual emissions. And by the end of the year, we're slightly on the emissions side, about 10 metric tons of carbon emissions, but very close to carbon neutrality based on the balance of hourly grid emissions, which was a really interesting finding. And then when we compare this to the best scenario, a slight improvement. We're still not quite at a net carbon emissions based on this hourly balance, but just incrementally better, slightly better. So now we can compare this to, well, first we'll take those operational emissions based on that mid-case Cambium scenario. We'll project this out till 2050, and we can see the annual metric tons of greenhouse gases over 5,000 metric tons based on the natural gas boilers and the grid emissions for our baseline. As we add PV, slightly better, but we do dramatically better by moving to that best scenario that goes all electric with heat recovery. We see those efficiencies, we see the benefit of the reduced grid emissions, and then slight improvements for the best. So capturing the net change, again, a little bit of benefit with the PV adding to the baseline, but over 5,000 metric tons of greenhouse gas emissions saved by the better and best scenario. And we wanted to compare this now to embodied carbon. We're increasingly looking at this at all of our projects. And so we developed these three scenarios where the high scenario might be a business as usual if we're not really targeting carbon emissions at all. And we attempted to capture all of the carbon emissions associated day one with the development of this project. Often we're looking just at structure, maybe the envelope starting to look at site emissions. We got some data from AEI who've been looking at MEP systems. We studied the PV systems. So we tried to get an all-in number. Sometimes you see an embodied carbon intensity for commercial buildings around 400. When we added in all the different aspects, and here the site is considerable because this is a suburban site. We're considering worst case that we're taking a northwest forested parcel, a greenfield, with trees and making it a parking lot and a building. There are some considerable carbon emissions associated there. So that, 400, if we said was core and shell, when we conclude all in, including a pretty intensive MEP system, we talked about the ventilation systems, conditioning systems required, close to 1,400 kilograms per square meter. Now, if we reduce the carbon emissions associated with the concrete and the structure and optimize the envelope, maybe typical best practices, we can reduce that to just over 1,000 kilograms per meter. And if we do best practices, which is looking at mass timber in an existing site, we could almost cut that by 50% to just about 800 kilograms per meter. And potentially there's certainly some other materials we could look at to even further drive that. So these are all day one carbon emission savings. And I want to point out two things. One is that the magnitude of these embodied carbon savings from day one by doing these best practices are the same magnitude as 25-year accumulated operating greenhouse gas savings. So that's not to say that those future emissions and the operational savings are not important. They absolutely are, but that embodied carbon is just as significant, and particularly in a region where we have a relatively clean electrical grid and getting cleaner, that embodied carbon increasingly should be part of the conversation for holistic sustainability. And the other thing I want to point out is that with these embodied carbon savings, a lot of these are possible without increased cost. We've worked on mass timber projects with Swinnerton where we found them to be cost competitive to steel. We can certainly reduce the embodied carbon with smart choices on the envelope at no cost premium. So, and we can procure lower carbon concrete often at no cost premium. So these are definitely things that should be looked at and potentially implemented at zero or negligible cost. Okay, with that, I know we're close to the hour. I'm going to quickly just recap some of our conclusions here. And as we saw, net zero energy is technically possible in outpatient facilities, and the caveat is with large site areas. So this is our suburban scenario. Again, we had about 11 acres of site, considerable area for PV. So it is possible, but for defining net zero energy as being able to provide that energy just on the rooftop, not possible based on our 2 or 4 story scenarios. The building is just too energy intensive to do that. But what we saw is that it is challenging from a life cycle cost perspective. This is not to say that energy efficiency doesn't pay back. We all have seen and believe that it does. Part of this is how we packaged our bundles. I think by sort of unpacking these things, some of these changes were more operational in base. Some of these we can further refine, but based on these packages and based on our high level assumptions for maintenance cost, they did not pay back within this scenario. So I think, any one project, we want to look at this much closer and to find the best package that makes sense for the client in terms of energy efficiency. I want to point out too that we uncovered, based on the types of renewable energy we looked at, that they're very variable, both in the day one cost, but also in the environmental impact. And I think increasingly, as we start to balance operational carbon emissions with embodied carbon emissions, we need to really make the best choice informed both by first cost, life cycle cost, and life cycle carbon emissions, and we increasingly get better data to do that. And then finally, while we dove into this project really around net zero energy, I think one of our bigger findings is that decarbonization is probably the most appropriate goal for this type of facility, but most projects that we're doing, really looking at holistic decarbonization, understanding the trade-offs between operational carbon and embodied carbon, and really working with our utility partners to understand the future of energy and how our project can really optimize, meet the programmatic needs, meet the day one and operational cost needs, but also look at how it can be sustainable in the future is really important. And so we want to look holistically at decarbonization, both operationally and from an embodied perspective. And with that, and we are exactly at 1 hour, I want to leave with one quote from Dr. Margaret Chan, who is the executive director of the World Health Organization, making the point that really a healthy planet and healthy people are really aligned on two sides of the same coin. So we really appreciate the support of Energy Trust to dive into this, to speak to you all. And we'd love to take questions now, if we could.
Wonderful. Well, thank you, Chris. Well done, right on time. So yeah, I want to thank you and the whole team for being here and bringing kind of all the perspectives that it takes to pull together a project team. So it's great to have you all speaking to your areas of expertise. So I'm going to start with some kind of general questions and then get into the more technical ones and then close this out a little more broadly. So first, a softball question, and this could be for any or all of you, which is what surprised you most about this research?
I'll start, and I'm sure my colleagues will have answers too. You know, I think I was surprised and a little disappointed about the finding that that, you know, based on how we defined our parameters, that there wasn't a financial payback. I think we're expecting that the better scenario would look better. You know, I think we've kind of dialed into some of the reasons. You know, and you know, I think. You know, definitely would look at that more deeply in practice, but that, you know, was the one surprise. I think the other was that those embodied carbon savings were so significant compared to operational. We've seen that in other projects, but the grid is so clean, and kind of looking at getting it cleaner, you know, that was pretty dramatic to me. I'll sort of open it up to my other colleagues to see if any other reactions there.
I think I was most surprised about the delta between the better and the best. I think I naturally expected the best scenario in all of those configurations to really be linear in comparison with the better and base. So that was a surprise to me, because I just assumed the investment would pay off, and it's not so.
Anyone else? Any other surprises? Well, I guess related.
Here, Naomi, I think one of the interesting, and Philip touched on it a little bit, was that flattening of the increase as you got up to that better and best scenario. Now, it is related to the number of windows in there, and I think, you know, we worked on a project with ZGF and AEI where there was a big emphasis on environment of care, not only for the patients but for care providers, and that comes with lots of daylight into the spaces. So it's worth noting that there is a trade-off there, but there is a potential savings for going more energy efficient, having less fenestration, less windows, and more opaque surface. But as Chris, you know, so, you know, thoroughly kind of reviewed, is there is other options there that could prevent different types of value.
Yeah, thanks. And I guess the related question. I've been background noise. The related question that's come up then is, I guess, based on those surprises or the research more broadly, how will this change how you work with your clients or the recommendations you make to them?
You know, I don't think it changes anything. I think it reinforces, I think, and gives us more ammunition, if you will. One, to, I think, really look closely, kind of be able, I think in the course of a project, we would disaggregate all of the you know, individual savings and be able to look at them more closely. You know, we're still looking at packages, and but I think being able to investigate those, and I think the other thing, as I mentioned, we've been largely focused from an embodied carbon perspective on structure first. We have a lot of tools to look at envelope and assemblies, but recognizing both that the site and the MEP components are so significant, that's, particularly in a mechanically intensive typology like this, that just gives us, further encouragement to increase the scope of our embodied carbon studies and really looking at the implications and data related to those types of systems. Wonder if AEI or have any other conclusions there.
Yeah, I was going to say, it took me a minute to think about what surprised me, but I think for me, I did expect the premium sort of delivery system, the active chilled beams, to perform better compared to the VAV with reheat and just the regulatory requirements for the high air changes, even though we could put ACBs in some areas, really made that improvement small, especially compared to when the plant side changes we could make, especially when we got the heat recovery chillers on the plant side. Those were able to make up for a lot of the simultaneous heating and cooling improvements that we got from reducing the airflows with the active chilled beams. So we weren't seeing as much savings because the heat recovery chiller can sort of make up for that to a large extent in the better scenario. And so I think for me, the big takeaway here was that I'm really going to be pushing for some of those operational improvements. There is definitely resistance on the owner side and on the operations side to doing things like overnight setbacks in healthcare in ORs. And so I think doing the push, I'll be wanting to do more education and do more working with the clients to improve their level of comfort in doing things like overnight setbacks in ORs, because that is a very minimal to no cost, and it has a really high improvement in the efficiency.
And one more thing too, as far as how we work with our clients or the healthcare market at large, we really wanted to sort of show the impact of program. When you talk about sort of non-hospital facilities in the healthcare space, there's such a wide range of what an MOB or an outpatient facility looks like. So we really wanted to kind of illustrate the range and try to tease out what some of those drivers and key characteristics were. And so, yeah, we hope that will really be useful when working with our clients.
Yeah, and I just wanted to add to Lyle's point is that the relative cost of these is great, but not as great as it would be in a hospital environment. So there was no bar chart for constructing a hospital with these improvements, but it would be significantly taller in that histogram than these. So I think the general move towards outpatient facilities is making this a more feasible discussion.
And I'm just curious from, you all work in, this building type in this sector. Are you seeing clients ask for this level of analysis? Is this sort of are they having these conversations, or is this still pretty new and you're able to sort of bring themes from this research to them, which feels like new content to inform their decisions and, factors to go into their decision making?
I think there's a lot of interest, but the ability to invest in this kind of research is limited, and excited that this bridges that gap for a lot of clients, I think.
In Washington, a lot of this discussion is being driven by the Clean Buildings Performance Standard, and so the requirement to meet that EUI and with it in existing buildings, and they reduce it by 15% for newer constructed buildings. And Oregon is in the process of passing legislation for an analogous act. I forget, the name is escaping me right now, but we're going to have the same sort of EUI requirements coming through in the next couple of years, and I think that will drive a lot of this discussion here as well.
Absolutely. I'll just mention that the online report that addresses both the Washington standard and the emerging expected limits for Oregon. And I also say, just to your question, Naomi, I think there's a range. I think we've worked on projects with this team where we've looked at things sort of, at this level or aspired to, and then we've had some, definitely clients, as Jenny's talking about, where we haven't. So I think this report helps kind of fill in the gap and start that conversation.
Thanks. Okay, so I want to move us into some more technical questions. So I think a couple for Katie and Lyle, and I'll maybe ask these both together. I think it's just kind of clarifying some of the assumptions. In the improved cases, were the windows also improved beyond the base code case? That's one. And then the other is the $8 question about the $8 a watt for rooftop solar. Does that overall cost include labor, the inverter, and interconnection, all of that? So 2 questions probably for the AEI team.
And architecturally, before you go there, Katie, I'll just note that the windows, we do assume an improvement in the frames and glazing between the baseline and the better. And then we actually go to triple pane glazing in the best scenario. So there is an incremental increase assumed for the window component.
Then I think I would defer to Eric and Philip about the cost of the site-mounted PV.
Yeah, I think that was that
Turnkey.
unit. It is turnkey is the answer, but I think the unit rate you quoted, Naomi, is for site PV, not for rooftop.
That's right.
Okay.
Yeah.
About half of that for rooftop.
Rooftop. Okay.
But it does include the installation of the structure and the PV panels themselves.
Great. Okay. Hopefully that answers the question. If it doesn't, feel free, whoever put that one in there to clarify. Okay. And then another question for Swinnerton on the life cycle cost analysis. Did that include the ITC federal tax credits for geothermal or solar systems, or the 179D tax deduction? So that's the investment tax credit. Are those factored in?
Yeah. Well, I can answer that because we did the actual life cycle costing. All of those were disappearing as we were doing the report, so anticipating that, but seeing that those things going away. And I think geothermal, you could still, if you're putting in a system in the next couple days or something, maybe you could still take an incentive, but sadly currently those incentives are disappearing, so did not include any of those incentives, just the energy trust incentives.
Okay.
Yeah, and typically the Swinnerton and I think our design partners as well would support the application and submission for any credits that are available based on the build, but as best practice, don't often include those in our cost analysis.
That's good to know. Interesting. Okay. And then a couple questions about the carbon analysis. So for projecting operational emissions, curious why you use the AER rate instead of the LRMER rate from NREL's Cambium.
I looked at a number, I think there are 8 or 10 different rates, and was looking at what seemed to be the best representative to me in terms of, and there was like a direct carbon emissions and there was an equivalent carbon emissions. And I thought I captured that, but I would be happy to learn more about this. And if there's the LNR rate is more appropriate, I'd love to be educated more, and we can adjust those if necessary. But I did look at it for a while and felt like I had the right number, but acknowledging that there's a lot of data and it's a fairly technical tool. But yeah, I would love to be contacted and discuss this further.
Okay, and another carbon question I'm going to try not to butcher. Have you evaluated any sorbent technology for these types of projects with high air change requirements? Reduces the outside air requirements by scrubbing CO2 and VOC from recirculated air. That's something you're aware of or considered?
Yeah, it's kind of more of filtration, right? So type of, then I ask Lyle or Katie if we looked at that. I mean, it seems like it's a mechanical side, potentially energy storage and recovery.
Yeah, we did not look at that within the scope of this study. That's still, really more sort of bleeding edge to the market, and we're what a lot of our healthcare providers are willing to do. So we did not look at that in the study.
Yeah, the use of active chilled beams in certain areas and the induced air changes to meet the air change requirements, we had specific experience with getting that approved through certain AHJs, and so we were comfortable including that in the premium system. But that was sort of as far as we were pushing options in terms of things we knew we could probably get into the mechanical design if we had a conversation with the AHJ.
This team has presented last week in Salem, or some of the folks on this team presented in Salem and Medford. And Katie, one of the things you were talking about in Salem was increased efficiency standards for hospital-specific equipment. And there's some interest in that. I'm wondering if you can share a little bit more about the research you've done there and how that relates to overall performance.
Yeah, I know that I did some research for this based on, I did several hours of research, not a ton. I would love for someone else to expand the scope of doing research specifically on imaging technology. So I found several studies evaluating how much energy is used by things like MRIs and CT scans in in this sort of hourly use, and I adapted that a bit for an outpatient setting. But I know that there is an Energy Star label available for some imaging equipment like MRIs. And so I would encourage people to look for MRIs that have the Energy Star label. And I know that that label is new, like it's within the last year, the version that I was reading about. And so I don't know how much availability there is on the market currently. And I don't know how much it is really going to improve it compared to the standards that were already being met by the existing equipment. One thing that I will say about imaging equipment is something we've consistently seen is that MRIs usually have their own standalone cooling equipment, both for redundancy, because that equipment is MRIs are so expensive and they want the uptime to be seamless, basically, so you can have very, very high utilization of an MRI machine. And so something that can be a challenge in these designs is I want the process heat from the MRI to be available for heat recovery on the plant side. And that's something that often is a little bit of a sticky point in the design negotiation with operations. They sometimes want the standalone chiller. They don't necessarily want it to be hooked up to the main chilled water loop. And so that's something like the operational setbacks that is something I push for because I really want that waste heat available for reuse in our climate.
And just to pile on a hair, I mean, we think about the process, there's the medical and imaging equipment. We're also food service is common in some of these facilities. And then the sterile processing department is another really big target where we can look at lowering energy, lowering carbon, recovering and reusing that heat that Katie's talking about. And also there's significant water savings to be had too. So those are some of the different kind of process realms we try to look at.
So related to that, this is a question any or all of you could answer. If you had another research grant, what would be next for this body of work? What would you want to dig into next to advance it?
That's a good question. I think there's two threads. I mean, one, I think there's a number of things that we couldn't get into just in the scope of the study in terms of really dialing into that sort of cost effectiveness. I think I would probably look more closely. I think we're so focused on getting to net zero energy that we didn't necessarily kind of look at the optimization of those strategies within that. So maybe not setting so far, but looking at the optimization both from a cost and a carbon perspective. I think the data suggests there's a lot of potential for optimization within both of those criteria. So that's where I would take it.
Yeah, and I would just add on just a little bit that pulling those components apart individually to understand them individually is intriguing architecturally, because when you bundle them all together, you see only the sum. So that would certainly be one thing I'd like to look at. But I would also be interested in looking at more the I2 hospital setting with this same kind of strategy and setup.
I would say that, there's so many assumptions that are necessary in a broad-based study like this. It's a great intro, but really it just, I think one of the slides that Chris shared showed how we went from suburban and urban, Portland and Bend, good, better, best, and the ASC and the MOB and the ASC plus MOB. I mean, and you could continue breaking down that tree, level upon level upon level. And so if you start from the opposite side of let's have a net zero building and then let's build out the program to meet net zero, what can we put in the building that already meets net zero? I think that would be an interesting study. And we could adjust the square footage. We could adjust the program to meet what we needed it to meet. And so I think that would be the reverse approach almost would be an interesting study.
I love that. If only there was a healthcare institution or a client that wanted to work that way, right?
Yeah, goodness.
Any other thoughts, Kyle or Katie, or Lyle or Katie, on what else you'd study?
I think for me, it's mostly on the process side. So looking more at the imaging and sterile processing department loads. I think those were areas I felt pulled towards and just didn't have time. Yeah.
I think the carbon data too on MEP is also still emerging, and as that becomes more available, it'll be interesting to see how that plays a part, especially as we, pull things apart to make them more efficient and optimize them the best we can. Is there a cost related to the carbon that we pay for that, and when does that balance?
Yeah. So I think just a couple more questions. Folks are curious if any of these findings are relevant to other building types, or what will you take away from this to bring to other projects?
Yeah, I think on some level, I mean, this is we talked about sort of the programmatic range and, within the type and the diversity, but in general, I think it's a similar dynamic and similar set of strategies for other high ventilation building types. And so, one area we work in is labs. Now there's lots of unique aspects and operational aspects of laboratories that are different than medical office facilities. But I think some of those same sort of strategies apply, definitely sort of more mechanically intensive. And I do think that the carbon conclusions are, other than maybe the intensity of mechanical, are fairly translatable to other building types for this particular grid region, recognizing that we have the dynamic of really clean energy at a really low cost relatively for the US.
In addition, I think other building types might benefit even more from the envelope improvements, where we're really fighting against the intensity of the programs driven internally. So the deltas between making these improvements might actually be greater for other building typologies. We're really looking at the extreme sort of end of a particular building type.
Anybody else?
I was also thinking about labs, Chris, when Amy was asking a question. So I think it's a high ventilation space. There are high internal loads. Often the sort of base lab might not have super higher change rates, but if you have any kind of clean room, or there can just be other scenarios when you have very high ventilation rates in certain areas of a life sciences building. So yeah.
Maybe just add sort of the approach that the research team took to this question and this proposition, as far as understanding how climate and program and sort of urban, how that impacts the energy use and the feasibility of some of these goals, approaching low energy design by reducing the demand first and applying passive systems, low energy systems, and trying to find that sweet spot. And then, kind of considering cost and energy and carbon and sort of the life cycle in addition to first cost. And so, I think all of that can be applied to other building topologies as well. The conclusions might be different, but sort of the approaches that this integrated team took to this challenge and this problem is what we'd like to see, break down the barriers of different markets and building types.
That's great. I love that. That's super helpful and replicable or scalable. Okay, so maybe one last question before I hand it over to Kriya, because we have 2 Energy Trust Net Zero Fellows on this call, and we're soon going to be announcing our open application. Any recommendations you have for folks that are thinking about applying for the fellowship and doing research like this, from Chris or Katie or anyone?
Do it. Get your friends involved, friends and colleagues. That's a great opportunity, and there's so many, I think, challenges in the sphere, and there's so much, a little bit of change and uncertainty right now, I think, sort of from a policy perspective, but so much opportunity, and we have so much understanding of where we need to go. I think it's a great opportunity, and I also think there's still so many other sort of typologies and challenges that we need to learn more about. So it was a great opportunity for sure.
Yeah, I had a fantastic time on both projects that I've had the opportunity to work on for Net Zero Fellowship. And I would say that my biggest piece of advice for people coming into it is to be really mindful of your scope. I think there were plenty of moments when I felt really overwhelmed doing my project, and the moments when I made a lot of forward progress, or when I gave myself permission to narrow something and say, I do not need to look at that. I am looking at these things, and there will be enough here to be useful to the public, because I felt a large obligation to make my research as broad and as useful as possible.